Okay, this is the assignment that was called Force Diagram number 4, continued. I got an elephant standing on a ramp, of course. Draw a force diagram to determine the components of the elephant's weight parallel and perpendicular to the ramp. So just draw a force diagram. It's just exactly like this, except the ramp's going this way. So I'm going to try as best as I can to make a nice dotted line that looks like it's parallel to. I started out a little too steep there and tried to correct. That looks pretty good. And you can use a ruler for this, of course. I probably should be doing that too, but freehanded enough of these things in my time. There's the elephant. See his little trunk there? Just kidding, it's just a dot. So there's force of gravity on the elephant. Now, when I go to label it, I'm going to think about, before I put the label, before I write it down, I'm going to break this up into those components. I could even draw them in now if I wanted to. I know I'm going to go X, just like you're trying to plot a point and get to here. X, Y. That's my right angle there. So since I'm putting those over here, I'm going to put the label over here. This is the force of gravity on the elephant from the entire Earth. And since the elephant has a mass of 2,000, that means its weight, or in other words, the gravitational force weight, same thing, is 20,000. Multiply that by 10. Okay, I don't know why I made two equal signs there. That's weird. Okay, and this is 20 degrees. So where's the 20-degree angle in this triangle? Well, if you draw it nicely, 20 degrees is obviously the smaller angle, so that's got to be this one. Like, that's not a 20-degree angle, that's the 70. Right? If you draw everything so that it looks like 45 degrees, then it's hard to tell where your angles go, so don't do that. All right, so this right here is 20,000 times the cosine of 70, or 20,000 times the sine of 20. Up to you. And here's another thing. I mean, you got to use a little bit of common sense and pay attention here. I'm going to do 20,000 on the same screen here. I'm going to do 20,000 sine 20 and 20,000 cosine 20. There's the two components. Right? There's one that's about, let's say, 6840, and let's say this one's 18,800. Right? 6840 and 18,800. Now look at these two. Like, obviously this is the bigger one. So no matter what you're thinking about angles and stuff, this is definitely the 18,800, and this one is definitely the 6840. So don't be labeling like longer legs of triangles with the shorter number or the smaller number. You are smarter than that. So now this elephant is just standing here. So forces are balanced. That means there must be a support force or normal force on the elephant from the ramp. That must be equal to this. And there's a friction force. If there's no friction, the elephant's going to slide down that ramp. So there's a force of friction on the elephant from the ramp, and that's equal to this, 6840. I think the first time you see force diagrams like this, when things are on ramps, it's like, oh my goodness, this is like hard trig and stuff. But if you practice them, they're all the same. It's really not that bad. So if you're feeling stressed out about them, don't worry. You just practice after you do about, I don't know, I think even like 10 of them or something like that, and if you're thinking to yourself, well, you're not giving me that many, Mr. McGrath, well, practice doing the same ones. Just redo them. All right, Tarzan. Have you heard of Tarzan, Lord of the Jungle? Prepares to swing, and much to his dismay, his loincloth got stuck on a branch. He's left hanging with the vine pulling upward here, and the loincloth pulling back, or the tree pulling back this way, and of course gravity this way. So there's Tarzan. Now there is not a ramp here, so the axes, it's not like the rock and elephant. It's not like these, because Tarzan is not on a ramp. So that means the axes are just going to be straight across, straight down, or straight up, depending on how you look at things. Let's see. Well, gravity doesn't really care what Tarzan's doing. There's still the same gravitational force on Tarzan from the entire Earth, and I'm not going to look at these questions yet. I'm just going to make the force diagram. So I'm scanning through here to figure this out, and it looks like Tarzan's mass is not mentioned until here. But we do know it. It's 75, so times 10, 750 newtons. Now, the vine is pulling up this way, and this is pulling that way. So I'm going to try to match that angle as best as I can, and that is going off into one of my quadrants, so I'm going to have to do my components X and Y like that. Now this is the 40-degree angle here, so this is 50, that's 40, and then the loincloth, or the tree, is pulling back this way. So that's a force of, I guess we could call that a force of tension. It's kind of like a rope, sort of. Force of tension on Tarzan from the, if we're really doing forces on him, then the loincloth is pulling on him, right? From the loincloth. If you said it's from the tree and you're kind of considering it to be part of him, that works too. That's fine. I'm not going to fuss at you about that. Could these be balanced? Sure, because this would be equal to this, and then this would be equal to this. So this component here, that's got to be the 750, right? And then it seems like maybe we're kind of stuck, but I think we could do more with trigonometry here. Let's start answering these questions, and then we'll come back to the diagram and fill everything in. Write an equation for the vertical forces on Tarzan. So the equation would be the force of gravity. When I write my equation, I'm going to drop the extra subscripts because that gets a little bit too much, I think. So the force of gravity is equal to, you could say equal to 750, but what we want here is not numbers yet. The force of gravity is equal to the tension. If this is the force of tension on Tarzan from the vine, then this is equal to, I guess I should call this is T1 and T2, so I don't get them mixed up. T2 will be the loincloth, T1 will be the vine. So that's equal to the force of tension from the vine, but it's not the whole thing, it's this part of it. So I'm going to say that that's times the sine of 50. It's opposite to this, times the sine of 50 degrees. That's what we're looking for here, the equation that just says this equals this. But I want to do it in terms of the names of the forces. Write an equation for the horizontal forces. So this is the force of tension from, that's T2, the loincloth here, is equal to this, which is the force of tension here, and it's the cosine component, cosine of 50. Those equations are very important. Those equations just say, in like the language of math, what our diagram says. This equals this, and this equals this. All right, Tarzan's mass is 75 kilograms. Find his weight. Weight is the same as gravitational force. We already did that. We multiplied by 10. All right. Use the appropriate equation for the forces on Tarzan to determine the tension in the vine. The tension in the vine is T1. So that's from this equation right here. So now I'm going to put numbers into this. I know that the force of gravity on him is 750. The force of tension in the vine is I don't know what. That's what we're trying to find, times the sine of 50. So that means the force of tension in the vine must be equal to 750 divided by the sine of 50. And just to make sure we're paying attention here, if this is 750, this better be more than 750, because duh, look at the triangle, right? This is the leg of a triangle, so I don't know what this is, but it's definitely got to be more than 750. So if you get something less than 750, then you got to go back and look at what happened, because you screwed up. So 750 divided by the sine of 50 is 980, I'm going to call that. And then here, determine the tension in his loincloth. We got two different options here. I'm going to go ahead and use this equation here. But you could also, now that I know this, you could do some trig to find that using the 980. That's also an option. I'm going to do it from this equation here that says, oh, I guess I am going to do it that way because that's what my equation says, doesn't it? So force of T2, that's what I'm looking for, is equal to force of tension in the vine, which now I know is 980, times the cosine of 50. Right? So it's that number times cosine of 50. It's about 630. Right. If that seems real hard, well, it's, I will tell you this. Problems in this unit right here aren't going to get any harder than that. So if you can manage your way through that, make a nice diagram. Obviously, making a good diagram is so key to being able to do these. All right. Number 8. A 90-kilogram skier takes to the slopes and reaches a constant velocity. Okay? Constant velocity means forces are balanced. If something is at rest or moving at a constant velocity, then the forces are balanced. Draw a force diagram for the skier. I'm going to try to match that slope. And make my other axis perpendicular to that. Get out your ruler if you want. Going to make your diagrams real pretty. It does help an awful lot to have a good diagram. All right, so gravity doesn't care. Now that I know that since this is on a slope, I know that just like the elephant and the rock, numbers 5 and 6 from this assignment, I know I'm going to have to break up this force of gravity along these lines, literally. So I'm going to do that right now so that will just help me. I don't want to clutter up the diagram too much by accidentally putting that force of gravity and then having to draw lines through it. So I'm going to put my label on this side. Force of gravity on the skier from the entire Earth. Yes, so that's just reminding us that it is like the rock and the elephant. Okay. 90-kilogram skier, so that means force of gravity is going to be 900. See how I can multiply by 10 like that? And since the skier is going at a constant velocity, the forces are balanced, which means there must be a support force. Call that the normal force, means perpendicular. On the skier from the slope or the hill or whatever you want to call it. I'll say hill. And that is going to be equal to this. I haven't done the math yet here. I'll do that in a minute. And then there's got to be a force of friction on the skier, also from the hill, or from the snow, whatever. I'm going to fuss at you about that. And that's got to be equal to that. So let's see. In my triangle, where's the 35-degree angle? It's here, right? That's the skinnier angle, and this would be 55. So then you can do your sine and cosine whichever way you want, but obviously this is shorter than this. So don't do anything that I wouldn't do. So 900 times, I'm just going to do them both, sine 35 and 900 cosine 35. You could have done it with a 55-degree angle too. So the 737, that's obviously the bigger one. And then 516 here. So that means this must be 516 because it's matching that, and this must be 737. So I bet I answered all these questions here. I just need to fill in the answers. Determine the skier's weight. Weight and gravitational force, the same thing. Determine the component of the skier's weight that must be supported by the hill. So that was this. That's the force of gravity times the sine of 55, or cosine of 35, whichever angle you wanted to use there. And that was equal to 737 newtons. Right? That's how much must be supported by the hill. Determine the component of the skier's weight pulling the skier down the slope. That's this. So that's the force of gravity times either the cosine of 55 or the sine of 35, depending on which one you used. Both correct. And what's the total force of friction and air resistance acting on the skier? Well, it's got to be balancing that. So force of friction is 516. If that threw you off, like friction and air resistance, and you're like, what, air resistance? Well, we just rolled all the frictional force into one thing here. So that's all we're looking for.